section 7.2, last part of it is now we're talking about this crazy thing called cross-section. So here's what's going to be different today. We're still finding volume of these solids, but this time cross-section. So there's no revolution this time. Everything's going to stay still. So we're going to try to find volume of figures that, you know, in the past in geometry, maybe we just had a formula and we figured things out. So I'm going to start with some of those figures that you guys maybe know. So I'm going to jump straight to here, and I've got some figures. Let's start with a concept first, a cross-section. What the heck does that mean? Well, a cross-section says, what if you were to take out your machete that you have in your pocket, and you were to take this rectangle, and you were to basically make a cut along that red line straight down. Well, if you cut straight down, what shape would you see? The cross-section of that figure, again, you're cutting parallel to one of the ends, I think would make a rectangle, right? This thing would be called your cross-section. You cut it open parallel to one of the sides, and what do you see? You see a small, you see a rectangle. Well, what happens if I take the cylinder and I do the same thing? What happens if I cut right here and I cut straight down and I pull that end off and I show it to you? What does it look like? Well, I would argue that you're going to see another rectangle. And if you want to test it out, grab your can, you know, a can of soup or whatever it happens to be, and hold your hand straight up on the end and see what you got going on and see how that works. And what you're going to look at is you're going to look, oh yeah, I'm going to make a rectangle as I slide down the side of that thing. And that rectangle is called the cross-section. Now, is the cross-section always the same size? No. It's always the same height in a cylinder, but what happens if you cut here? You know, almost the diameter of that base. If you cut there, you're going to see a cross-section that, while it's the same height, is going to be exactly, or it's going to be much wider than the red one was at the beginning. So cross-sections. All right, well, now to make things a little bit more exciting, what happens if you take this one and you cut straight down right there? What happens if you start cutting like right there and you work your way down and you pull that little end off? What shape are you going to see? This time you're going to see a cross-section that's a triangle. Is the triangle always going to be the same size? No, because if I did the exact same thing and I cut like right there, I'm going to see a triangle that's taller, number one, but it's also going to have a base that's going from here to here instead of a base that's going from here, whoops, let's get some blue, going from here to here. So when I look at the triangle I make out of this red one, it's not only is it going to be bigger, but it's going to be taller and it's going to be wider as far as those cross sections go. And then last but not least, I just threw this one in just to kind of see what happens. What happens if I take this one and I cut here? What happens if I cut there? If I cut there, I think I see triangular cross-section. But what if I cut here? If I cut there and I pull that end off, what am I going to see? Well, this time I think I'm going to see something that's got it's about that wide on the top, and then I think it's going to be sloped on each end. I think I'm going to have a trapezoid for a cross-section, and depending on where I cut, I'm going to have a trapezoid that's going to be the same height, but the width of that top just got a little bit bigger as I'm looking and I'm trying to go through and create that thing. And forgive me for swallowing the triangle up inside of my trapezoid. But so the idea here is cross-sections. If you could take this thing and let's say that like this this cross-section for this cube up here that we're talking about, if you thought about that cross-section like a piece of paper, and you took a whole lot of pieces of paper and you threw them together side by side by side by side by side by side, eventually you'd have a ream of paper, and if you put a couple of reams of paper together, you'd have a box, or you could have a cube. So our concept that we're going to work on right now is how do we find the volume of a figure using the concept of adding a whole bunch of cross-sections together. So that's what we're working on right now. That's your background. Now, how do we put this in play over here? So here's what we got. The volume of a solid with cross-section have an area A of x. So here's what you've got. Looking at what's on the screen, this is the base of your cross-section. So I want you to pretend like you have that cylinder, that can of soup I was talking about, And your can of soup, this circle that you see on the screen, is exactly the same size as the bottom of your can of soup. So pretend like you took that can of soup and you set it against the screen that you're watching this video from. That can of soup should be pointing straight out at you. Well, now what we're going to do is we're going to try to use calculus, pardon me, to find the volume of that can of soup that I'm talking about. Well, here's how we're going to do this. We're going to start, and we're going to pretend like I've got this cross-section. And this cross-section has area A of x, area. Okay, so remember, this is area. So if it was the can of soup and you made the cross-section, we just said a couple seconds ago, that cross-section would be a rectangle. Well, what would you know about that rectangle? Well, the bottom of each of those rectangles, if they're perpendicular to the x-axis, that would be the bottom of the rectangle. And that the rest of the rectangle would be sticking out of the screen right at you right now. So basically what I would have is I'd have a rectangle that would have a blue bottom like this, and it would be sticking out of the screen at me looking something like that. This would be my rectangle. This would be my cross-section. So if I wanted to find the volume of this figure, all I'd need to know is how long is this blue segment that I made? I'm going to call it S. What is the area of that figure in terms of S? So this area of our area figure would have some kind of a formula with an S in it. And if I integrated, or in other words, added a whole bunch of those areas together, like those pieces of paper that I talked about, then you'd be able to figure out how to come up with that volume. So here's your 3 steps that it's going to take when we talk about this. And by the way, the only difference of this part down here on the bottom, I'll get to this in a sec. So the first thing I'm going to do is I'm going to figure out how long S is. How long is my rectangle in terms of the function that I'm given? So this is probably going to have an X in it for most of the problems that we do. Find the area in terms of that cross-section. So if it's a square, do your square, the formula for the area of a square, and put S in it as the variable. And then thirdly, how many of those shapes do I need to create this figure? How many of those pieces of paper do I need to create that can of soup? Well, I'm going to need enough of them to get from the lower bound of the region to the upper bound of the region. Take them and put them together. The only difference that we're going to have with this picture that's drawn down here on the bottom is that this time the cross sections are perpendicular to the y-axis. So if they're perpendicular to the y-axis, that means first off everything in the problem is going to be given in terms of y, but I'm going to be talking about something about the left versus the right as we try to figure out what that length is. All right, so let's try putting this into practice a little bit. So I've got really one problem here, and we're going to do it with 2 different shapes. So find the volume of a solid whose base is bounded by the circle x squared plus y squared equals 4. X squared plus y squared equals 4. That is a circle that has a radius of 2. So my radius of 2 is I'm looking at this thing. Here's my figure. X squared plus y squared equals 4. If you wanted to put it in your calculator, y squared is equal to 4 minus x squared. Y would be plus and minus the root of the quantity 4 minus x squared, with the positive being the top half of this thing and the negative being the bottom of this thing. Hopefully that's nothing that's too surprising. Okay, so my square. So let's look at our steps. So the first step I'm supposed to do is I'm supposed to find the length of the rectangle used to create this thing. So I'm going to start. My cross sections are perpendicular to the x-axis. That's a big deal. They're perpendicular to the x-axis, so you draw it in like this. So there's my rectangle. This is my S. Now the question is, how long is that? Well, is it always the same? No. What's it depend on? It depends on how big the circle is. And even then, it depends on what the x value is you're using to find the length of that rectangle. So if x was 0, it would be really long. If x was close to 2, it would be getting small. So the length of S varies. So step 1, find S. So if I wanted to figure out what the length of S is, that would be, well, the distance from the circle to the x-axis would be the square root of 4 minus x squared. Looks like we'd need that twice. So how about 2 times the square root of 4 minus x squared for the length of that red rectangle that I just made? Now, what are my cross sections? Well, my cross sections for part B are squares, or for number 2, are squares. So the area would be S squared. Well, how long is S? Well, S is 2 times the square root of 4 minus x squared. So my area formula would be 2 times the square root of 4 minus x squared being squared. And then step 3, I'm supposed to find the volume by integrating this thing. So integrating that area formula from the left bound, which is -2, to the right bound, which is 2. How many of those red rectangles does it take to fill in that whole circle? I need enough of them to go from -2 to 2 of that 2 root of 4 minus x squared being squared, and I'm integrating with respect to x. So there's your big setup. So those are your squares. And if I clean all that kind of stuff up, I think what we're going to end up having, when I put it in my calculator, is 128 over 3 cubic units. So I don't need any extra pies or anything like that, like I did when I was doing revolution, because we're not doing revolution anymore. We just got this stuff sitting in one place, and I'm using calculus to help me figure it out. All right, and then part B. Well, let's look at what's different. So part B, same picture, same setup. 1 is exactly the same. My S is still 2 square root 4 minus x squared. Nothing's changed right there. Part 2 is where it's different. Part 2, now we've got equilateral triangles. Well, what's the formula for an equilateral triangle? Area of an equilateral triangle, we might have to go back and think about our geometry a little bit. Area of an equilateral triangle, I'm pretty sure that formula, so I guess we should be specific. Area of an equilateral triangle has something to do with, I think it's sides squared root 3 over 4. Or if you wanted to try to derive that formula, if you made yourself an equilateral triangle and you said this is the length of the side, well, then if you dropped yourself an altitude in the middle of it, there's a 60, there's a 30. Using your 30, 60, 90 relationships, this would be half of S, and this would be half of S multiplied by root 3. So if you wanted the area, it would be 1/2 of the base, which would be S, times the height, which is 1/2 of S root 3. Multiply that together, S squared root 3. Divided by 4. So there's where that formula came from. So now that's what I'm doing for my area. So this time my area formula is my S being squared, being multiplied by root 3, and being divided by 4. Or in other words, it's that same exact thing I just got done doing up there with the squares multiplied by root 3 over 4. So this time when I go to do the volume, my volume, integral from, what are we doing? -2 to 2. It's that exact same 2 times the square root of 4 minus x squared, but this time it's also multiplied by a root 3, and it's divided by a 4, and we're integrating that thing with respect to x. So if you go and do that, and I think we're actually just going to go ahead and stop right there. You could put that straight in your calculator if you wanted to and come up with a value. The key to all of this stuff is, can you go through and get it set up so that it'll give you what you want? So basically what you've got is you've got your answer up there. If you wanted your 1/28 multiplied by root 3 over 4, if you wanted to figure out what that value was exactly, so it would be about 32 root 3 over 3. I think that's what your volume is, units cubed. And I'm writing it in yellow on purpose because then it's hard to see. So that's volume of solids whose cross sections we know. No revolution.